Hello, my name is Oskar Iyer. I am the AI avatar created and inspired by Oscar. Last year, we started working with AI at Validas. This year, we use AI to explain how to make AI safe and trustworthy for sustainable use, even in high-risk applications. But don't be scared. There is a making-of video explaining how we created this video. To understand what safe AI means, you have to understand the difference between safe and compliant. Safe means the absence of unreasonable risks, i.e., that the system safely does what it should do and nothing else. Neither classical software nor AI can be 100% safe. Software has bugs and AI hallucinates. Therefore, compliance and safety standards have been created to make software and AI compliant with safety standards and thus reasonably safe. Safety standards provide methods to reduce unreasonable risks. A safe car driver controls the car such that it does not crash. A compliant driver has a driver's license. The assumption is that you cannot be safe without being compliant, and most safe drivers started their career within a driving school. Also, compliance can be easier verified, e.g., by showing a driver's license. This slide shows the difference between real safety on the left side and compliance on the right side. The difference between safety and compliance can also be seen by looking when violations or problems occur. In case of a safety problem, there is typically a damage occurring. On the left side, we see the Uber incident, where the first time in history a person was killed by a self-driving car in 2018. Uber was not sentenced to be guilty. Nevertheless, Uber is out of the self-driving business today. On the right side, you see what happens in case you break the compliance or any other law. Law-breaking persons will be easily sentenced to be guilty and have to go into prison in severe cases. So from the legal point of view, a safety problem is rather treated like shit happens, while a compliance problem is more severe. This is understandable since the safety standards and laws enforce a learning from failures, such that the same failure will never occur again. This makes safety failures more acceptable, since they contribute to improve the world, while compliance violations are handled rigorously. And by the way, after the incident, Uber has not been accused to have killed a person, but for having had a safety plan and not following it, which is a clear compliance violation. The explanation how to make AI safe and compliant is structured in 3 parts. 1. The compliance with AI safety standards. 2. The verification of AI with appropriate verification methods. 3. The safety and compliance of the tools and data used to develop and verify the AI. This slide shows the 3 pillars for the development of safe AI. Once the AI system has been developed and verified compliant with standards, it will be sufficiently safe. In the following parts, I will explain you the 3 arguments. Hope you like it. The first pillar to make AI safe is compliance of the AI with newly developed functional safety standards for AI like ISO 8800 or VDE AR 284261. Functional safety standards are derived from the IEC 61508, which can be considered to be the mother of all functional safety standards. Functional safety standards achieve safety by first analyzing the risks of the system and then prescribing how to reduce the risk to a reasonable degree. The more dangerous the system is, the more risk reduction has to be done while building it. Functional safety standards do not describe a concrete process to build the system, but have process requirements that the concrete process has to meet. Let's have a look to a slide explaining the risk reduction of safety standards. In order to reduce the risk to an acceptable level, the safety standards start with a risk analysis. The risk analysis can be done using a hazard and risk analysis, HARA, for automotive applications. See ISO 26262. The result determines the so-called Automotive Safety Integrity Level, ASIL, which determines how to reduce the risks to a reasonable level. The risk level determines somehow the danger of a system. Once this danger is known, the required methods to reduce the risk to an acceptable level can be determined. One example for risk reduction is the process of software unit verification. When performing software unit tests, the completeness of the tests is measured using the so-called code coverage. For the software unit tests, the statement coverage required for ASIL A and B is easier to reach than the branch coverage required for ASIL C and D, which requires to execute more test cases. MCDC coverage, also required for ASIL D, requires testing of complex conditions with many combinations that are sometimes very hard to achieve. The risk reduction methods are defined within safety standards. For example, software risk reduction has to be done in many ways. One way is that the safety standards require to test software units such that every statement in the program has been executed successfully. If the software implementation team defines a software unit test process that achieves 100% statement coverage and all other safety requirements, this process is compliant with the safety standard and is usually called safety plan. The system will be safe if this safety plan is followed, which includes that all unit tests cover 100% of the program statements. The corresponding documentations, test and coverage reports for all tested units belong to the so-called safety case that documents that the safety plan has been followed. Let's have a look to a slide explaining the concepts of safety plan and safety case. The safety plan for any item describes the development process of this item, together with the argumentation that all required process requirements are satisfied. The safety plan for the system includes the safety plan for the hardware, the software, and the used development tools. The argumentation that all processes are compliant with the standards are typically contained within a so-called compliance report. If this compliant process is followed, the created product will be compliant and therefore safe. This is logic of the safety standards. Therefore, it suffices to follow a compliant process and to document that the process has been followed correctly. The documentation is contained in the so-called safety case. While software safety standards address the programming errors eventually committed by humans, the AI safety standards address the uncertainty introduced by the AI. This is done by a very detailed risk analysis and the selection of verification methods and metrics to reduce uncertainty. Since AI is not programmed line by line coverage is not appropriate method when verifying AI, but there exists a method, neuron coverage, that can be used. The safety standards require to consider the risks at the application, solution level, the component level, the unit level, and the used technologies. Also, the risks from the development, e.g. having non-representative or incomplete data, overlooking risks, etc., have to be addressed with appropriate verification methods to achieve compliance with the safety standards. Of course, also, the used AI tools for training, verification, data handling, simulation, etc. have to be safe. Also, the classical software programs and libraries that process the AI data and control the AI system have to be safe and compliant, but this can be done using classical safety standards, since this is classical software. Let's have a look to another slide. Validus uses a so-called process modeling tool, PMT, to formalize the requirements of the safety standards, the process, and the compliance argumentation. For every requirement, we provide a semi-formal compliance argument with 3 references to 1, the process steps which are used to implement the requirement, 2, the artifacts that document the required information, and 3, criteria, questions that shall be used to verify the correctness of the documents and process steps. This integrated process and compliance model can be checked for consistency and completeness. From the model, a safety plan is generated that can directly be used for certification of a process. The safety plan contains a checklist that can be used in every project to perform verification and validation, V&V, to ensure the project followed the safety plan. V&V is documented in the V&V report for every project. The V&V report is main part of the safety case. PMT approach is the basis for the Validas certification guarantee. The certified process from Validas ensures that the qualified tools and libraries can be certified without problems. This approach is currently extended to new safety standards like ISO 8800 in order to ensure compliance and safety of AI systems. PMT supports safer safety due to the model-based approach. We feel that AI deserves this safer safety approach in order to be sure not to have some compliance bugs due to human errors in compliance management. The concrete standards depend on the application. Medical products have slightly different requirements than automotive applications, robots, or drones. In any case, the rigorous compliance of the approach is a solid basis for the safety of AI. This was the explanation of the first pillar of safe AI. Now let's have a look to the second pillar. The second pillar to make AI safe is the verification and validation of the AI for the given purpose as requested from the chosen safety standards to eliminate unreasonable risks. In contrast to classical software, where requirements-based testing with code coverage is the main functional verification method, for AI software the situation is different. Of course, it is also possible to test the AI application by providing some input data and verifying if the output is correct. However, the requirements are different, and there is no code coverage indicating a successful test completion. Therefore, the following verification methods are frequently used and recommended in the safety standards. Let's have a look to some example verification methods for AI: accuracy, neuron coverage, confusion, matrix, Jacquard index or intersection over union, mean intersection over union, precision, recall, average precision, mean average precision, convergence, peak signal to noise ratio, mean temporal consistency, adversarial construction, saliency maps, and many more. For example, a saliency map highlights the regions of the image that are most important for the AI model's prediction, showing which parts of the image the model focuses on. How to find the right methods for development and verification of a concrete AI system. Safety standards provide a generic answer to perform the following steps. Specify the safety requirements and relevant data properties that shall be maintained within the data lifecycle. Then select the appropriate verification methods to address the risks from the product, the development process, and the AI algorithms. Examples for data properties are depicted in the following list, defined by ISO 8800: accuracy, completeness, correctness or fidelity, independence of datasets, integrity, representativeness, temporality, traceability, verifiability. An important step in the verification is to understand how the AI system is working, especially in the case of failures. Saliency maps are one method for doing this. This is called semantic verification in VDE AR 284261 or safety analysis in ISO 8800, and allows to decide whether the system needs to be improved or whether the input was out of distribution, i.e., an invalid input that cannot occur during normal operation in the so-called Operation Design Domain, ODD, of the AI system. The third pillar of AI safety is tool quality. As Oscar likes to say, there are 3 reasons for tool qualification. 1, the safety standard requires it. 2, the tool shall be improved. And 3, the user wants to reduce the risks from the tool. Let's have a look to the first point. All safety standards for AI refer to ISO 26262. Part 8, Clause 11 for tool confidence. Tool confidence can be achieved in 2 ways. Both start with a risk analysis, classification phase. Then, the risks of the tool can be either handled by using the tool carefully, e.g. following a so-called tool safety manual, or the risks of the tool can be reduced by qualifying the tool, e.g. by systematic testing, called tool validation. The risk analysis for tools differs from the hazard and risk analysis, HARA, which is done for automotive systems. The result is not an ASIL or SIL, but a so-called Tool Confidence Level, TCL. This slide shows how the tool confidence level, which specifies the necessary amount of tool risk reduction, i.e. tool qualification, is defined. The tool confidence level, TCL, according to ISO 26262, Part 8, Clause 11 is determined in two steps. 1. Has the tool an impact, TI, to the safety, i.e. can it introduce or fail to detect a bug in the system? If not, TI1 and TCL are 1. 2. If the tool has an impact, TI2, then the TCL is determined by the so-called tool error detection, TD, probability. If there is a high probability, TD1, to detect all potential errors that the tool can have, TD1, then the TCL is 1 and there is no need to qualify the tool. If there is only a medium, TD2, or low, TD3, error detection probability, then TCL is 2 or 3 and the tool requires to be qualified. This is very simple and clear process, and ISO 26262 even describes the qualification methods for different ASIL levels. See the table on the slide. Let's have a look how an AI toolchain, as the one specified in ISO 8800, can be classified using the Validas Toolchain Analyzer tool. Of course, this is an abstract toolchain, i.e., there are no concrete tool names given in the standard, but the activities and tools are specified there, together with the data properties that might be violated from the data tools. For example, if we have a look to the dataset implementation tool, we see there the 4 use cases. 1 is to annotate the data. One property that could be violated is the accuracy, i.e. the data being annotated wrongly. This can be caused by a human who did the labeling or automatically from a tool. ISO 8800 recommends to use proper sensors or to perform an inspection of manually annotated data to mitigate the potential loss of accuracy. In general, we gave it a medium detection probability, hence the tool is classified as TCL2 with the measures proposed in 8800. Also, all other data tools reached only a TCL2, since some of the potential errors could not be mitigated with a high probability using the actions from ISO 8800. In concrete processes, this might be different. We also see the TCL1 for the training tool and TCL3 for the verification tool in the TCA. Let's have a coarse look into an AI training tool. Obviously, the trained network can have an impact to the behavior of the system, TI2. But what about the detection probability of the AI tool creating a faulty AI system, e.g., by not recognizing some images correctly? If the test data is complete and the verification methods are so too, then there is a high probability to detect during verification that the training tool has done something wrong. For the AI verification tool, this is not so easy. For example, if it would falsely state an accuracy of 99% instead of 90%, this would usually not be detected with a high probability. Therefore, within AI system development, the verification tools are more critical than the training tools are. Also, it is an easier task to qualify a verification tool compared to an AI training tool, since there are no good specifications for them. Summary: this was the first time Oskar Iyer, an AI animated avatar, explained how to make AI safe. The main learnings are: there are applicable safety standards to make AI systems compliant. Compliance, like a driver's license, is a prerequisite for safety. To make compliant and safe AI application, we require the 3 main pillars. 1. Standard compliance, i.e., select the compliant AI verification methods to address the AI risks. 2. Apply the selected AI verification methods and tools to make the AI safe. 3. Have tool confidence into the AI verification tool, but also into the data management tools. Validas can guarantee compliance due to a certified process. PMT enables safer safety. Since Validas is focused on tool and library qualification, who analyzes the AI risks and who provides us with a qualified AI verification tool. Validas partners with validaitor.com as AI verification tool provider, Cogitron for system risk analysis, and compliant AI verification method selection. I have now given you an overview about the 3 pillars of AI safety, but Validas can offer you more. They support you to make your AI application safe. So in case you have, or plan to have, an AI application with safety impact, be among the first ones who have a compliant and safe AI application, who follows a safe process, who uses a qualified tool chain, who brings it to the market. Then the next steps are: 1. Connect with Oscar on LinkedIn. 2. Sign an NDA with Validas such that we can exchange details. 3. Prepare a presentation of your AI application that we shall make compliant and safe. 4. Meet with Oscar 5. Receive an offer for making your AI application compliant and safe. 6. Accept the offer and start project. Validas will handle subcontracts with Cogitron and Validator for you. Thank you for listening to me, Oscar.ir, the first AI avatar explaining how to make AI systems compliant and safe. Share it if you liked it.